Okay, first, something briefly about the unit of acceleration, meters per second squared. So, you don't square the time here in the unit of acceleration. Whether you fall for 1 second or 2 seconds or 3 seconds, you don't square the time spent falling here in the unit of acceleration. But you square the time when you're trying to calculate the distance traveled in free fall, when you're falling in gravity. So here you square the time. If you fall for 5 seconds, for example, here you put 5 squared, 25. And I think this formula for the distance is pretty nice because it sort of resembles the kinetic energy formula. 1/2 times something squared. And you can try this to check that this gives the correct results. This is probably not the way you calculate the distance, but I know you can calculate the distance. You also get correct results, so you can check that this formula works. Gives the correct results. And the fact that this resembles the kinetic energy formula might be something to think about. But yeah, that was it about the unit of acceleration. Then let's talk something about momentum.
Hey, you can try again, but that's just crap. That's just you saying so. You can't show me a single piece of evidence demonstrating it to be true. So just show me one example of a Newton's cradle where 50 comes in here and 50 comes in here and it just stops. Nothing happens. Nothing out. Zero. 50 minus 50, zero. Show me that.
Nobody's going to show you that, and nobody believes that would happen. The problem here is that that is not conserving kinetic energy. I don't know how you missed that because it's sort of an essential part of the kinetic energy theory that you have been arguing against for quite some time now. But anyway, let's take a look at this simple case. Two identical objects colliding. Here we have 50 momentum. Let's say this is the positive direction. So here we have minus 50 momentum. Before the collision, the total momentum is 50 minus 50, that is 0. And yeah, of course, one case that would conserve this total momentum would be the one where the objects just stop moving. But then you would lose all the kinetic energy, so that can't be the case. And we know that this is what would happen. The objects would just bounce back, change direction. So then we have minus 50 on this side and 50 on this side. And the total momentum is minus 50 plus 50. That is still 0. So the total momentum was conserved, but now we are also conserving kinetic energy, as we should in an elastic collision. When I was thinking about these objects colliding, I started to think about what happens to the center of mass of the system. And I would also like to hear your thoughts on this. So, if we first consider just some object traveling in space, no matter what the shape is, no matter how it's rotating while it's traveling, I suspect that the center of mass will always be traveling a straight line with a constant velocity. So if we assume its mass is the total mass of the object, we can say that it is conserving its momentum in an isolated system. I think this is what conventional physics is saying, and I also assume that you would agree with this. So what I'm wondering is that what do you think would happen to the center of mass in a system like this, where two objects are colliding? And let's assume its mass is the total mass of the system. Will the center of mass conserve its momentum after the collision? What do you think?
You deliberately evaded it, frankly. I mean, I could read my email, but I pointed it out clearly that your biggest burden is to explain what happened to the momentum you created. If you're going to claim there's free momentum there, extra momentum, you have to explain what happens to it. Where does it disappear to? Because gravity is going to give it back 100%. And you have to account for its existence, now that you've created it. All right. So enough of that.
Yeah, I'm sorry I didn't address the point. It's just that I think there's a bit of a problem. What you're really asking me to do is to explain some aspect of kinetic energy theory to you. Because the so-called extra momentum or its disappearance, they follow from the conservation of kinetic energy. And any explanation I could give to you, any good one anyway, of course, must lead to kinetic energy. It must be in line with the kinetic energy theory. And I suspect that you won't accept any explanation leading to kinetic energy for that specific reason that it leads to kinetic energy. So you are basically starting with the assumption that kinetic energy can't be true. So any explanation leading to kinetic energy can't make any sense. This assumption of yours has been quite evident, for example, with the spring launcher experiment done by Stephen Brough. Because initially you said that that is the experiment that will settle the matter once and for all. Then Stephen did the experiment, got results in line with kinetic energy, and your conclusion was that it's a crap experiment. Or at least that Stephen was somehow doing it incorrectly, because his results didn't match with your expectations. And I think it's pretty much the same with the air carts. So first you were saying that Professor Lewin is lying to us about the masses of the carts. He's cheating with the masses. And then I guess you saw other people doing the same experiment, and you concluded that it must be the springs. So air carts with springs, that's some kind of special case. The only case in the universe where kinetic energy takes place. And you thought that it could never happen with, for example, Newton's cradle. Then there was the Newton's cradle experiment with 3:1 mass ratio. I did the measurements, and yeah, of course they were not perfect, but when they supported kinetic energy, you didn't even consider that they might be true, but you thought that there must have been something wrong in my measurements, because they led to kinetic energy. Then there was also the coupled oscillator experiment done by yourself. It's just that you didn't do any measurements, because apparently it was too obvious that kinetic energy wasn't conserved, but only the total momentum, the way you define it, was conserved. But again, Stephen Brough did his measurements from your video, and I'm not saying anything about how good his measurements were, because I have no idea about that. But his results again supported kinetic energy. I don't know if you have responded to that video by Stephen Brough, at least I haven't seen that. And then there was this one comment from you. I don't remember in which video it was, but you were saying that if somebody has an experiment proving kinetic energy, then there must be something wrong in that experiment. That's what you said. So I don't think there will ever be experimental evidence that will be good enough for you, because you have so strong intuitions about the laws of nature. But why should the universe be intuitive to us? Especially considering that our intuitions are largely based on both our Darwinian history and our very limited everyday experiences. So our intuitions can easily lead to wrong conclusions. If you want to do real science, if you want to have these scientific debates, I think the first step to take is to at least consider the possibility that you might be wrong. Okay, that was it. Bye.
You came here for a good argument.
No, you didn't. You came here for an argument.
Well, an argument's not the same as contradiction.
Can be.
No, it can't. An argument's a connected series of statements to establish a definite proposition.
No, it isn't.
Yes, it is. It isn't just contradiction.
Look, if I argue with you, I must take up a contrary position.
But it isn't just saying no, it isn't.
Yes, it is.
No, it isn't.